Hello, my name is Tatiana Ginjoun, and today's presentation will be on the topic of applied statistics. Today's presentation will focus on several key aspects of applied statistics, particularly in the context of Doctor of Nursing Practice DNP projects. It will begin by defining applied statistics and discussing its critical importance in enhancing the quality and rigor of DNP initiatives. Understanding key statistical terms relevant to DNP projects will be essential as these concepts support effective analysis and interpretation of data. To illustrate these principles, there will be a presentation of an example dataset to demonstrate measures of central tendency, specifically mean and median, as well as the measure of dispersion known as standard deviation. In addition, hypothesis testing and the significance of p-values will be defined by providing a practical example to clarify these concepts. To aid in understanding common pitfalls associated with statistical analysis, a slide would highlight frequent mistakes and strategies for avoiding them. Furthermore, there will be a decision tree for selecting appropriate statistical tests based on the type of data involved. Finally, these statistical methods will be applied to a DNP project example, highlighting how these approaches can effectively enhance project outcome. Applied statistics is a branch of mathematics that involves the collection, analysis, interpretation, and presentation of data. It serves as the foundation for data analysis, enabling organizations to analyze data effectively to identify and define their needs. Within applied statistics, there are two primary types: inferential and descriptive statistics. This field includes the formulation and explanation of research questions, leading to the creation of solutions that provide secure answers. Additionally, it emphasizes the development of reliable measurements and analytical methods to ensure the accuracy and validity of the insights that were found from the data. Applied statistics plays a crucial role in Doctor of Nursing Practice DNP projects for several reasons. It supports the principle of the use of evidence-based practice by providing the necessary tools for data analysis. DNP projects will involve the collection and analysis of both quantitative and qualitative data, and applied statistics helps the practitioners and students to summarize, interpret, and present this data effectively. Additionally, many DNP projects focus on quality improvement initiatives, and applied statistics will measure baseline performance, monitor changes over time, and evaluate the impact of interventions. Statistical process control tools are also valuable for improving healthcare processes. Understanding applied statistics is also important in designing research studies, as it guides to the selection of appropriate sample sizes, study designs, and methods for data collection and analysis. These factors help to minimize the bias and improve the reliability of findings. DNP practitioners must be skilled at interpreting statistical findings and understanding their implication for clinical practice. Knowledge of p-values, confidence intervals, effect sizes, and other statistical measures informs decision about the significance and relevance of research outcomes. Effective communication of findings is another important aspect, as the ability to analyze and interpret data ensures that information can be shared clearly with stakeholders. This includes healthcare teams, administrations, and patients. Finally, a comprehensive understanding of statistics supports ethical decision making in healthcare that will help practitioners assess the validity of research findings, recognize potential biases, and make informed decisions. An understanding of applied statistics is important for effectively analyzing data and interpreting results. Key statistical concepts frequently used in healthcare research and DNP projects include descriptive and inferential statistics. Descriptive statistics summarize and communicate the main features of the dataset using measures of central tendency such as the mean, median, and mode, as well as measures of variability like range, variance, and standard deviation. Inferential statistics allow researchers to conclude a population based on a sample database through hypothesis testing and estimation techniques. A main component of this analysis is the confidence interval, CI, which provides a range of values likely to contain the population parameter with a specified level of confidence, commonly set at 95%. Regression analysis will assist in estimating relationships among variables and incorporates methods such as linear regression, logistic regression, and multiple regression that enable researchers to assess how the dependent variable responds to variations in one or more independent variables. In examining the relationship between variables, the correlation coefficient, known as Pearson's R, measures the strength and direction of these connections. Researchers often use chi-square tests to evaluate the significance of association between variables. Then, when comparing means, the t-test is used, which has variance for independent groups and paired observations. For situations involving three or more groups, analysis of variance, ANOVA, is the appropriate method that allows for the determination of whether at least one group means significantly differs from the others. Understanding the statistical terms and techniques is key for effective research and practice in healthcare settings. The mean is a measure of central tendency calculated by summing all the values in dataset and then dividing by the numbers of values. It provides an average value that represents the data set as a whole. The median is another measure of central tendency, that is the middle value of a dataset when arranged in order from lowest to highest. If the dataset has an odd number of values, the median is simply the middle value. If it has an even number of values, the median is the average of the two middle values. Standard deviation is a measure of the amount of variation within a dataset. It calculates how much individual data points deviate from the mean. A low standard deviation indicates that the data points are close to the mean, and a high standard deviation shows that they are spread out over a wide range of values. In this dataset, mean 88.5, median 88.5, standard deviation approximately 6.02702. In statistics, a hypothesis refers to a statement or assumption about the population and provides a claim that can be tested through statistical analysis. There are two main types of hypotheses: the null hypothesis HO and the alternative hypothesis H1 or HA. The null hypothesis states that there is no effect or no difference within the population, as is used as a starting point for statistical testing. The main goal is to assess its validity. The alternative hypothesis suggests that there is an effect or a difference and represents what the statistical test aims to support. A main component of hypothesis testing is the p-value, which measures the strength of the evidence against the null hypothesis. The p-value indicates that there is the probability of observing the test results, or something more extreme, assuming the null hypothesis is true. A low p-value, typically less or equal to 0.05, suggests strong evidence against the null hypothesis, leading to its rejection, while a high p-value, more than 0.05, indicates weak evidence, resulting in a failure to reject the null hypothesis. To show these concepts, an example involves the impact of exercise on anxiety levels. The first is to formulate the hypothesis. The null hypothesis HO states that exercising does not lower anxiety, mean difference 0. While the alternative hypothesis H1 claims that exercise does lower anxiety, mean difference less than 0. After the formulation of this hypothesis, data is collected through a clinical trial that includes two groups, one engaging in exercise and the other not. After collecting data on the anxiety levels of both groups, a statistical test can be conducted, such as a t-test, to compare the mean anxiety levels. Upon analyzing the data, a p-value is calculated, which, for example, is a 0.03. Since this p-value is less than the significance level of 0.05, we reject the null hypothesis. This decision leads to the conclusion that there is statistically significant evidence to support the claim that exercise lowers anxiety. Common pitfalls in research include several important issues that can significantly affect the validity of findings. One major concern is the absence of an adequate control group, which limits the ability to make reliable comparisons. Researchers also may often fall into the trap of interpreting comparisons within two effects without actually comparing them correctly. This means that conducting separate pre- and post-comparisons for each group and merely looking at the p-values from those analyses is insufficient, as both effects need to be compared directly. Additionally, inflating the units of analysis can lead to misleading results, mainly when the study has a large number of subjects, because greater degrees of freedom can often downplay the size of significant effects when multiple trials are conducted. Another common issue is the confusion between correlation and causation. Researchers should avoid assuming that all correlations imply cause and effect relationship. Also, using small sample sizes can skew results, as smaller samples generally require larger effects to be considered statistically significant. Circular analysis or double-dipping presents another challenge, where hypothesis testing should always be conducted on a separate samples that did not inform the initial hypothesis generation. Finally, the flexibility in analysis, often referred to as p-hacking, allows researchers to manipulate their analysis plan for significant effects, which will affect the results. It's also important to address the tendency to over-interpret non-significant findings. The failure to reject the null hypothesis does not imply that the null hypothesis is correct, as the absence of evidence is not considered evidence of absence. This is a decision tree used to determine which statistical test to apply, either a chi-square test or a correlation regression. The tree first assesses the relationship between the variables and identifies their types. If both variables are categorical, nominal, a chi-square test is appropriate. However, if the variables are in interval or ratio in nature, a correlation regression test should be used. The project, titled Provision of Asthma Action Plans in the Primary Care Settings, a team-based approach by Lynn M. Hutchinson, aims to enhance the integration of asthma action plans within healthcare settings. The guiding picket question for this initiative is: does an education program on the fundamentals of the team-based care workflow process for the integration of asthma action plan intervention to healthcare providers of various disciplines population increase the number of plans developed for patients' outcome 4 weeks after the education program timeframe? A Microsoft Excel spreadsheet was used to compile data collection, and the collected data was analyzed using the MC-Nemer test. Additionally, descriptive statistics was used to assess participants' demographics. The non-parametric McNemer test is appropriate for this project, as it allows for pre-test, post-test comparison when involving two independent variables with nominal measures. In conclusion, applied statistics is an indispensable tool for enhancing the reliability of doctoral nursing practice DNP projects. Preparing practitioners with the skills to analyze and interpret data effectively creates informed decision-making and evidence-based practice in healthcare. A knowledge of both descriptive and inferential statistics, along with a clear understanding of key concepts such as p-values, confidence intervals, and regression analysis, helps DNP students and professionals to make meaningful connection from their research. Also, the ability to communicate findings effectively ensures that information reaches stakeholders, which promotes quality improvement and better patient outcomes. Overall, applied statistics not only strengthens DNP initiatives but also supports ethical and clinical practice that can make a positive impact on the population.